In July 1962, over the dark Pacific, a brilliant artificial sunrise bloomed above the clouds, silent and unreal. It was not the aurora, not a star. It was humanity testing a nuclear weapon in near space and discovering something disturbingly unexpected. 17 years earlier, nuclear weapons had ended a world war on Earth. By the early 1960s, they had become central to a tense standoff between rival superpowers who were now looking upward, wondering whether space itself could be turned into a battlefield. Right now, every phone call, bank transfer, and weather map already depends on the environment above our heads. The same physics that shapes auroras also controls the electricity flowing through your home, linking your daily life to invisible processes in near-Earth space. This is the universe and beyond, and today we are looking at the moment humanity literally nuked near space. We will see why Starfish Prime shocked scientists, rewrote space law, and convinced governments to stop sending nuclear weapons upward. In the early 1960s, the United States organized a series of high-altitude nuclear tests called Operation Fishbowl. The goals were bluntly practical and scientific, measuring whether such weapons could disable missiles, scramble communications, and reshape Earth's surrounding magnetic environment. On 9th July 1962, a Thor rocket rose from Johnston Atoll carrying a 1.4 megaton warhead, around 500 times the yield over Hiroshima. 27 smaller-sounding rockets followed, packed with instruments to watch what would happen to space itself. The warhead reached roughly 400 kilometers above Earth, about the altitude of the International Space Station today. Up there, the air is extraordinarily thin, the sky is black, and our planet below fills half the view like a glowing blue marble. When the device triggered, energetic particles streamed along Earth's magnetic field lines into the atmosphere. Over the Pacific, curtains of artificial aurora unfurled, visible from Hawaii to New Zealand, painting the sky red, green, and violet for minutes on end in eerie silence. In Honolulu, the cloudy night suddenly looked like dawn. For about 6 minutes, shadows appeared, colors returned, and people could read newspapers outdoors. Radio stations faded, some alarms sounded unexpectedly, and dozens of streetlights and electrical systems abruptly failed without any visible local cause. The test did not happen in isolation. The early 1960s were among the most tense Cold War years, as the United States and Soviet Union competed in missiles, influence, and spaceflight, after the Soviets launched both the first satellite and the first human. Military planners imagined nuclear devices on rockets that could intercept incoming warheads far above cities. Others considered whether weapons placed permanently in orbit could threaten targets anywhere on Earth. To evaluate these ideas, they needed numbers, not speculation, about how space nuclear use actually behaved. They were especially interested in the electromagnetic pulse, or EMP, created when a nuclear device releases a burst of gamma rays. That radiation can shake electrons loose in the atmosphere, creating powerful electric and magnetic fields that upset unprotected circuits over huge regions. Starfish Prime was only the first successful shot in Operation Fishbowl. Within months, more high-altitude tests followed, with names like Checkmate, Bluegill Triple Prime, Kingfish, and Tightrope, each tuned to probe different layers of atmosphere and different military scenarios. Some devices were similar in yield to the bomb dropped on Hiroshima, around 20 kilotons, and were fired from below 80 kilometers. Others, like Kingfish at 95 kilometers, crossed into what space agencies define as true space above the sensible atmosphere. In the vacuum of near space, there is almost no air to transmit sound or create a mushroom cloud. Instead of a roaring blast wave, a nuclear device there becomes a rapidly expanding sphere of plasma and radiation, coupled directly into Earth's magnetic environment. Just a few years earlier, in 1958, the Explorer 1 satellite had revealed intense natural radiation belts around Earth. These torus-shaped regions, now called the Van Allen belts, trap charged particles from the solar wind using Earth's global magnetic field. Starfish Prime unexpectedly pumped huge numbers of additional energetic electrons into those regions. New artificial radiation belts formed, stronger in places than the originals, and some persisted for years. Space near Earth became harsher almost overnight, with satellite components exposed to much higher doses. Several early satellites suffered. Britain's first satellite, Ariel 1, experienced severe damage and failed months earlier than expected. Telstar 1, the pioneering commercial communications satellite that carried live television across oceans, degraded rapidly within a year, its electronics stressed by the enhanced radiation environment. To understand the EMP, imagine those gamma rays from the device striking upper atmospheric atoms. They knock electrons free, which then race along curved magnetic field lines. The resulting current pulse produces rapidly changing electric fields that couple into long conductors like antennas and power lines. Because Starfish Prime occurred so high, the EMP footprint covered an enormous area. Hawaii, nearly 1,500 kilometers away, lost around 300 streetlights, had telephone microwave links disrupted, and saw security and communication systems malfunction, even though nothing physically touched the islands or their infrastructure. Scientists also released a tracer isotope, cadmium-109, when the device operated. Later measurements found traces of this material in rainwater as far away as New Zealand, confirming that debris from near-space tests could spread globally through atmospheric circulation rather than remaining localized. Starfish Prime was not even the largest high-altitude nuclear test. In 1958, an earlier shot nicknamed Teak, about 3.9 megatons in yield at roughly 77 kilometers, temporarily turned night into day and severely disturbed long-range radio communications across portions of the Pacific. The Soviet Union also conducted its own series of high-altitude tests, known collectively as Project K, over Kazakhstan between 1961 and 1962. Yields ranged from about 1.2 to 300 kilotons, at altitudes between roughly 40 and 300 kilometers above the steppe. One particular test, often labeled 184, took place around 290 kilometers altitude with a 300 kiloton device. The resulting EMP damaged a major power plant and reportedly caused failures along more than 1,000 kilometers of shallow buried electrical cables linking distant cities. These experiments taught both sides something sobering. High-altitude nuclear use could indiscriminately harm civilian infrastructure, space assets, and even neutral countries. Any attempt to exploit EMP as a strategic advantage risked also disabling one's own systems and poisoning the shared near-Earth environment for years. So, in 1963, the Limited Nuclear Test Ban Treaty was signed by the United States, United Kingdom, and Soviet Union. It prohibited nuclear tests in the atmosphere, in outer space, and underwater, reducing global fallout and halting further official high-altitude nuclear experiments. Further steps followed. In 1967, the Outer Space Treaty entered into force, banning placement of nuclear weapons or other weapons of mass destruction in orbit or on celestial bodies, and declaring outer space a realm reserved for peaceful purposes and scientific exploration. Today, our dependence on space infrastructure is vastly greater. Navigation, banking, aviation, agriculture, television, weather forecasting, and large parts of the internet all rely on satellites. The exact same orbital regions. Those tests disturbed now host the systems modern civilization expects to work continuously. If a similar nuclear device were used in high orbit today, enhanced radiation belts could disable or shorten the lifetimes of many satellites at once. Power grids, communications, and navigation services on the ground would suffer cascading outages far beyond anything seen in the 1960s. A natural event hints at what an intense electromagnetic disturbance can do. In 1859, the Carrington solar storm produced auroras visible near the tropics and induced currents so strong in telegraph lines that instruments sparked, sometimes continuing to operate even after being disconnected from their batteries. A comparable solar storm aimed at Earth today could, in principle, damage transformers and satellites through induced currents, similar in some ways to an EMP. So both technology and nature can shape our electromagnetic environment, though large solar events of that scale are fortunately rare. However, experts worry more about deliberate human actions than about rare solar superstorms. Recent debates have mentioned the possibility of a nuclear device placed in low Earth orbit as an anti-satellite capability, something that would violate the Outer Space Treaty's clear prohibition on such weapons. The Outer Space Treaty lacks strong enforcement mechanisms, but it still represents a shared understanding. Nations recognized that turning orbit into a nuclear domain would endanger all users of space. The environment above our planet is simply too interconnected to divide neatly into separate battlefields. The same gravity holding you to the ground also guides radiation belts, satellites, and missiles. The same electromagnetism powering your laptop drives auroras and empeffects. This is not separate physics in space, just the same rules playing out on larger scales. Starfish Prime revealed that space could be weaponized in ways that ignored borders entirely. Its artificial radiation belts and EMP impacts did not respect national boundaries, instead reshaping a whole planetary shell of near space and harming satellites belonging to multiple countries at once. This realization, combined with public concern over fallout and satellite failures, pushed leaders and scientists toward agreement. So we stopped testing nuclear weapons in space, not only to limit radiation on Earth, but also to preserve orbital infrastructure and maintain access to the space environment. Today we recognize near-Earth space as an environment to manage, much like the oceans or atmosphere. Crowded orbits, debris, radiation, and fragile satellites all interact. Introducing nuclear weapons, there would not be a contained experiment, but a profound alteration of a common resource. Instead, space agencies now use satellites to study climate, monitor storms, map forests, and peer deeper into the cosmos. These instruments turn orbit into a laboratory, not a battlefield, allowing us to understand our planet's systems and the wider universe with unprecedented clarity. This episode of The Universe and Beyond is part of a broader story about how humans first used space. There were also unexpected participants, like ambitious projects from smaller nations imagining lunar or even Martian missions. Explore those surprising histories in our other space history videos. We are made of stardust right now, living beneath shimmering radiation belts and orbiting machines. Starfish Prime reminded us that choices in space echo globally. Keeping nuclear weapons out of orbit is really about protecting one small, interconnected world and everyone who depends on it.